So that is there, right? Okay, we'll wait a few more minutes to see if people joins. Okay, fine. We have 3 people. We'll start. Right. So we have completed the chapter, chemical kinetics, but we'll just do a couple of problems. Okay. So this is the question. So they're telling the rate doubles when the temperature is changed from 300 Kelvin to 310 Kelvin, right? Okay, they're telling that the rate of reaction doubles when its temperature changes. Temperature changes from 300 to 310 Kelvin, right? What will be the activation energy for such a reaction? Go for it, right? So they're telling the rate doubles. What do you mean by rate doubling? That means the rate
A becomes
constant
2.
are double. Correct, right? So the rate constant becomes double. That's what you need to understand, right? So the rate doubles when temperature becomes from 300 to 310 Kelvin. What will be the activation energy for this kind of reactions? So there is just one equation you have to know. Whenever you have two rates, you know how to do it. Two rates, two different temperatures, right? Hope you know the formula. Hope you remember the formula. It's log K2 by K1 is equal to EA by 2.303 R into 1 by T1. Actually, it will be 1 by T1 minus 1 by T2. T1 will be less, correct, right? So R value you have to use just 8.314. Yeah, are we there? Yes, we are. Yeah, okay. So R value should be 8.314 because you're using in terms of joules, right? So just substitute the values, nothing else. Okay. So this will be log 2 because it will become K2 becomes double of K1. So I can
Sir,
write it as 2K1.
53.6 kilojoules.
I think it's correct, right? So this will become log 2. EA is what I have to find, 2.303 into 8.314. This will become 1 by 300. 1 by 300 would be, or say if I write it as T1, T2, 300 into 310 divided by 310 minus 300 will become 10, right? So 300 into 310. This is 93,000. 10 divided by 93,000. Okay, anyways, we'll keep it like this. So log 2 value is 0.3010 into 2.303 into 8.314 into 93,000 divided by 10 is what would have been your answer. I think it's correct. 53.6 kilojoules is what is the answer. Kilojoule per mole would be the answer. Okay, direct formula substitution. That's what you need to do. Okay, so I hope there will be no questions on this because direct formula substitution, right? Okay. Okay, one more question. So they're asking, they have given you a graph, the energy profile diagram. This is reaction coordinates. Okay, so okay, so the dotted line represents the reaction with catalyst. Okay, and the solid line represents without catalyst. And telling you this difference here is 2 units. You can keep it as 2 joules because this potential energy is in terms of joules. 2 kilojoules. Yeah, this is actually kilocalories. Right, potential energy is marked in terms of kilocalories. So the difference here is 2 kilocalories. Right. So they're asking you how much the rate is affected. The sense that they're asking you what will be the ratio of the new rate with respect to the old rate. New rate means with catalyst, without catalyst, that ratio is what they're asking. How many times the rate will increase? Go for it. So again, a modification of Arrhenius equation is what will you do, but with respect to catalyst. Temperature is given to be 300 Kelvin. This reaction happens at 300 Kelvin. So now in this case, temperature is going to be same, only the activation energy changes. So if you remember the formula, EA is what is going to change. So it will be EA by 2.303 RT, sorry, 1 by 2.303 RT into EA1 minus EA2. Basically, this is without catalyst, this is with catalyst. And this value is what is given here. This value is 2. Right? And hope you remember what R value I should use. What is the R value I should use here? What is the value of R? 2, because you hope you remember it is calories. If it's in terms of calories, we use R value as 2. If it is joules, I use 8.314. Right? So yeah, substitute it. Oops. Actually, they should have given you some anti-log values here. The only thing I'll be able to find. But in this question, it's not given, so you don't have to worry. Right? Whatever the log value, keep it in terms of log. Say I'll write log of K2 by K1 is 1 by 2.303 into 2 into 300 into 2. 2 and 2 gets cancelled. Right? So it is basically going to be 1 divided by 2.303 into 300. So approximately also I do. It will become so if it's 2, it will become 600. So it will be 600. Should I write it? So 23 into 3. 23 into 3 will become 46, 69. So can I say it will become 600, sorry, 690 point, sorry, 690 something, 690 point something. Right? So 1 by 690 point something. So 1 by 690 again will be a small number, right? So what you have to know, this is here log to the base 10. So you can write K2 by K1 as 10 to the power 1 by 690. You can keep it as such. Like they should have given you any anti-log values, but they didn't give it in any question. right? So keep it like this. Okay, 10 to the power 1 by 690 will be the answer to this question, right? Okay, actually there is a very small topic left in this chapter, but the questions will come, might come. Okay, fine. We'll look into it. Okay. Right. So now we'll see something about complex reactions, right? So remember, in kinetics or in general, any chemical reaction, right, can be classified into two types. One are what are called as your elementary chemical reactions or simple chemical reactions, and the second one is what is my complex chemical reactions, right? So what is the difference between these two? Is elementary reactions or simple reactions are single step processes, only one step. Reactants giving products, that's it, right? But complex reactions are going to be multi-step processes, right? So multi-step process in the sense they are made up of two or more number of elementary steps. Hope you understand, right? So elementary step is a single step, right? So what I'm telling you is complex reaction is a combination of two or more elementary steps, right? Now, what is so important about these elementary steps is this. Say if I have a reaction like A giving B or A plus B giving products, whatever it is. This is an elementary step, assuming that this is an elementary step. So you can write R is equal to K A power A into B power B. So what I'm trying to do, you see, generally we don't write like orders directly as a stoichiometric coefficients. We don't do it like that, right? But if the reaction is an elementary reaction, that if it happens in a single step, then the orders of the reactions can be their stoichiometric coefficients. Okay, so this will happen only for an elementary chemical reaction, right? You can take the orders, right? You can take the orders to be equal to the molecularity. Hope you know what is molecularity. Molecularity is the number of reacting species, right? So for an elementary reaction, order and molecularity will be same in the sense that you can directly take the stoichiometric coefficients as the order of the order with respect to that particular reactant. Okay, right. So that is one thing. But what happens to complex reactions, and that is where you will not be able to use like this. You cannot directly use the stoichiometric coefficients like this, right? So generally, we have so many types of complex reactions, but we will just see one of the types, and that's what's there in your syllabus, right? There can be. So what we are looking at is you are seeing reactants to products, but now we are going to look into the mechanisms. Obviously, that is where the number of steps will become increased, is it not? So if I look at the mechanism, say it can be a two-step process or a three-step process, right? I say if I go for SN1 reaction, it's a two-step process, something like that, right? Okay. So we'll try to understand what happens in a complex reaction, and we'll take only two steps, right? So remember the first step, like what we are going to take is always going to be an equilibrium step, right? And the second step will be the, say second step is a, like gray, okay. Okay, fine. Second step is a normal step, right? How will I write it here? So first one will be an equilibrium step, and this would be a rate step. I can keep it like this, whatever it is. Okay, so let me give you an example, right? So now see, I have two NO2 molecule reacting with O2 to form, or NO molecule reacting with O2 to form NO. Okay, NO2, sorry. Okay, right. Now this is the overall reaction, right? So if you look at the mechanism, what people suggested is like this. So they say that I have two NO molecules first forming N2O4. Okay, now this N2O4 reacts with O2 to form NO2. Okay, fine. Right. So if you look at this, right. So remember, this is actually whatever the N2O4 which I wrote here is an intermediate. Okay, this N2O4 what I wrote is an intermediate. So generally the first step will always be an equilibrium step. First step will always be a equilibrium step. And please understand, this is say it has a equilibrium constant of Kc, right? Say that this has a rate constant of K1. The second reaction, second elementary step, is having a rate constant of K1, right? Okay. Now you know that the slowest step, right? The slowest step is what is going to be the rate determining step. Hope you remember this, right? The slowest step is the rate determining step, and they should give you in the question which is fast and which is slow. Say 99% of times the second step will be the slow step, and the first step will be a fast step. Okay, not only in this question, first will always form the intermediate, whatever be the kind of reaction, and the intermediate reacts with the other reactant to form the product. So second step, the intermediate reacting with the product to form the other reactant to form the product will always be the slow step. But there can be differences. But if there are differences, we use different methods that is not there in influence. I go for something called the steady state approximation and all that. Anyways, right. So if this is given to you, right, how will you write the rate law of this thing? Right. Now, please understand, right, in the rate law, the equation which you're going to write, R is equal to something which you're going to write, right, there should not be any intermediates present. Okay, there should not be any intermediates present. What you see is only reactant NO and O2 is only present, right? So only those things should be there in the rate law equation. You should not be mentioning about N2O4. That's what is the thing here. Okay, so how will we do it? Let me tell you. Right. So if I take the RDS, rate determining step is this, the second step, right? How will I write? R is equal to some K2 is the K1 is the equilibrium, a rate constant, which will be N2O4 concentration into O2's concentration. N2O4's concentration into O2's concentration. No issues, right? Now, but again, you see in this, I have N2O4 present and I don't want that. What will I do? I'll go for the previous step. Now, if I write Kc from the first step, if I write the Kc value, how will I write? It will be concentration of N2O4 divided by concentration of NO squared, because I have two. Okay, N2O4 concentration divided by NO squared, right? So what I need is concentration of N2O4, right? So I can find it out from this. So this I can write as N2O4's concentration will be equal to Kc into NO square. Correct? Kc into NO square. Now substitute this here. What are you going to get? You're going to get R is equal to K1 into N2O4 is Kc into NO squared into. That's it. This is the rate law equation. Right? Because why? Because you see that there is no mention of the intermediate. Right? So this K, again, this Kc and K dash, I can together write it as some K dash, right? K1 and Kc, some other rate constant K dash. So how will I write it properly? R is equal to K dash into NO squared into O2. That is what is the rate law. Okay. So like this also questions can be asked. Nothing. This is how exactly the model would be. First step will be an equilibrium step. Second step will be the rate determining step. Right. So obviously in the first step you will have the intermediate. Second step you will have the intermediate reacting with the reactant to form the product. Right. So you take the rate determining step and represent it. In that you will have the intermediate. Go for the previous equation and get the intermediate in terms of the other reactant and substitute it. You are going to get the rate equations. Okay, we are not going to do any problems on this because the problems we might get are very, very rare. But even if you get, you should be able to do this. Just please make this, take this down. This will be the model for all the questions which they can ask from this particular area. Okay, so yeah. So with that, the chapter gets over. Okay. Right. Fine. So next chapter, what do you want to start? You have any preference for chapters? Okay, So
sir,
maybe we'll start
group elements, sir.
what?
Group elements, sir, like S block, P block, D and
Yo, no. See, even if I teach you, that will be the most boring thing you can ever do with me. Trust me.
sir, but like
Right?
that, how much weightage does that have, sir, in a paper?
Uh, See, the thing is, entire periodic table, see, in inorganic, I have other chapters also. See, what I'm trying to tell you is, you don't have to worry about the reactions part. Do not worry about it. Right? And all these reactions, S block, P block, and all these things, do not worry about the what is that reactions. Right? What you have to worry about is the trends. Right? Stability of the sulfates, how melting point varies, how boiling point varies, how is there any assumptions, right? Structure of molecules, right? All these are only important. Yes, you will get enough questions, but if you know chemical bonding, 50% of things you are already done. Because once you look at the molecule, even though you don't know anything about the group or whatever it is, but you know the atomic numbers, you know how to draw structure of the molecule. So if you're strong at chemical bonding, some problem is resolved. And if you're good with trends, like how atomic this thing varies and all that, right? Again, 80 to 80, 90, 90% of problem is solved. Other 10% is the assumptions. Again, if you know the atomic trends, assumptions is a must, which you know, which you should know, right? So this way you practice. Do not worry about the reactions. Just study your NCRT, but you should know top to bottom of your NCRT, in the sense that without the reactions, whatever they have given you, or there is a book. You can buy any book for the matter. Actually, any inorganic textbook, right? You try to get it for JEE mains, right, and just go through it. That's it, right? And there is a lot of things to remember. There's a lot of things to remember. That's the problem.
Or sir, can we directly look at previous year?
Yes, that's the easiest way to go about it. Take 20 years, 30 years, solve only those questions and go for the exam. Enough. First attempt is okay. Second attempt, more and more, like again, next time you go for the exam, little more you study about these chapters and then go for write the second exam. But again, I think it would not be necessary. Right? Just go for the previous year questions, see what they're asking, and prepare accordingly. That's it. That will be the easiest way to go about it. Right? So me teaching is like me reading you the book. It's exactly like that. Maybe I'll give you a little more information there and there, but not worth it. Okay.
Okay.
Right.
Okay.
Yeah. Again, your teachers only would have told, they would have also done the same thing. I guess they would have asked you to take the books with you, and they would ask you to underline whatever the important points, because there's nothing much we can do about it. That chapter, it's like a self study chapter, 90%, because now you know all the concepts required for you to understand this. You know, so you just have to go through and apply it. That's it, right? Okay. So other than that, which chapters you want to start? So we have electrochemistry, solutions, solid state. 3 are left in physical chemistry. Shall we go for electrochemistry?
Okay, sir.
Okay, fine. Okay. Okay, take down the question. Or maybe I will write it in small words. So they're telling resistance of a 0.2 m solution is 50 ohms, right? And the specific conductance of this is 1.3 Simon per meter. And they're telling if the resistance of 0.4 m same electrolyte solution is 260 ohms, what is the molar conductivity of this 0.4 m solution? What is the molar conductivity of this 0.4 m solution? Molar conductivity, you know, you write by lambda m, right? Okay. Now tell me which area this question is from electrochemistry.
Molar conductivity.
Obviously, molar conductivity, but there are other things involved right here. Fine. What is the formula for molar conductivity? Lambda m is equal to
K by C.
Yeah, lambda m is equal to conductivity divided by the concentration. Correct. Right. Okay. So conductivity is also called as
reciprocal of
specific
Conductance.
specific conductance, right? So just like resistivity and resistance, resistivity is called as specific resistance, like that. Conductivity is called as specific conductance, right? So what they have given you here is the specific conductance of this 0.2 m solution, not the 0.4 m solution, right? You have to find the resistance of the conductivity of the 0.4 m solution, and you know the concentration, then you can easily substitute here. So this is about how do you measure the conductivities. There is a setup which helps you measure conductivity. What is that? Or which helps you measure the resistance. What is that? Wheatstone bridge. Yes, in physics, Wheatstone bridge, I'll be able to use it for say any solids, something like that. But if it's electrolyte, like a liquid, what instrument, or I don't know called as an instrument, but a setup, what will you use? Yes, be confident, you're right. It's conductivity cell, right? So hope you know how a conductivity cell looks, right? Conductivity cell will look like something like this. Say I'll have glass made of, this thing, chamber made of glass, and I have the electrolytes, right? So here I'll fill the electrolyte, right? So this will be connected to the whatever the source you want to connect, right? So you know there will be something. This is the length, the distance between the electrodes is what is the length, right? And the area in between the electrodes is what is my area, right? So you'll be able to find, right? So first thing you have to find is the resistance of this. How will you find the resistance? So you take this and you go to the Wheatstone bridge. In one of the arms of the Wheatstone bridge, right, you attach this. What will you get? You will be getting the resistance of this particular liquid. After you find the resistance of the particular liquid, now you know L and A, right? So you can write rho is equal to R is equal to rho L by A, right? And this rho, I can write it as 1 by kappa, that is 1 by conductivity, right? So you know R from the Wheatstone bridge, and from this calculation, you will be able to find what is the K, conductivity, right? But there is one thing which I'm missing in all this. There is one important term which I'm missing. What is that? Now, all the things I told you, but this one thing I'm missing. What is that?
Cell constant.
Right. We're talking about the cell constant, right? So cell constant is this L by A, G star. We represent it. G star is nothing but for a particular cell, right? We'll not be able to measure it, right? So when you buy a conductivity cell itself, in that only it's mentioned G star is this much. Okay, so that's basically going to be L by A. So how will I write the equation now? So can I write R into K is equal to G star, as simple as that, because you write rho as 1 by K, so this goes here, and L by A is what is my G star, so I can write R into K, that is resistance into conductivity, is what is my G star. Okay, right. So now using the first data, resistance is given, specific conductance conductivity is given. So can you find G star? Right now you're using the same cell, you're not changing the cell. So the same G star will be used the second time. But in that time, what I don't know is the conductivity. I know the resistance. I know G star. I have to find the conductivity. After I find the conductivity, go for finding the lambda m. Go for it. Tell me the answer. Hope you understood what I'm trying to say. So basically, you have to use this formula 2 times.
So 0.1, sir.
Is the question 0.1? No.
So it is a 0.62.
0.62 makes sense, but I think you are missing some decimal points. Okay, we'll check. Right. So first, if I do this, R into K is G star, R is 0.2, and this is 1.3. So you'll be getting the G star as 13 into 2 will become, so it is going, can I say it's going to be 0.26, right? So 0.26 will be the G star. So now if I go for this one, and again I use, so in this case, yeah.
G star is resistance into copper.
Yes, sir.
G star resistance into
Specific conductance.
correct, resistance into specific conductance. Resistance, oh sorry, I did point to point. Okay, sorry. So 50 into 1.3, right? 50 into 1.3 would be 15 and
65,
30.
sir.
65. Yeah, 65, right? So 65 per meter. That's what you'll get, right? So now if I use it again for the second solution, so I have R, which is 260, into the K, which I don't know, which will be 65. So K will be 65 divided by, am I doing it correctly? Yeah, right? 65 divided by 260. Okay.
1 by 4, sir.
Yeah, okay. So it's 0.25. Right? Now this will be 0.25 Simon meter squared per, oh no, it's Simon per meter. Right. Okay. Then what you have to know is lambda m is equal to K by C. Now what you have to understand is, people, right? See, remember, this can be represented as Simon meter squared per mole. right? But what will you use the concentration as? Concentration will always be mole per liter, right? Concentration will always be mole per liter, right? But what I want is mole per meter cube, because everything is now here. You see meter is there everywhere, meter is only there. So mole per liter, molarity M, which you write, right, will be a small problem. So always what you do is, if you have the K in terms of Simon per meter, and if they ask you lambda M in terms of Simon meter squared per mole, always you multiply the numerator by 1000, just to make the convert liter into meter cube, right? I know 1 meter cube is 1000 liters, right? So like that you do. Now same thing will you do if it is given in terms of Simon per centimeter, and if this is asked in terms of Simon centimeter squared per mole, again you multiply by 1000, right? And they will not generally ask you giving meters and asking you in centimeters, that they'll never do, right? So either meters are given or centimeters are given, you have to put this 1000 here, or else the calculation will not come properly. Now why are we doing it? It's because I have mole per liter here, right? But everything is in terms of meters, so it is better to have liter in terms of meter cube, and that's why we are multiplying by 1000, right? So I think now you should be able to get the answer. This is where I think you would have missed your decimal point. Okay, so keep this in mind. This 1000 is very, very important. Okay, good. So what I was telling, so K value I found out, which is 0.25 divided by C for this is 0.4 into 1000 is what I'll do. Okay, right? So done. So 0.4 into 1000. 4 into 1000 will become 250. So this I can write it as 2500. So 2500 into 25. Right? So it is going to be about 6.25 into 10 to the power something will get. That's what you'll get. Okay, fine. I think the only thing which you don't know in this 1000 you have to put. Other than that, I think you know everything. Right? Fine. We'll go to the next question. Okay. So they're given a table, electrolyte, and it's lambda m naught, or I can even write it as lambda m infinity. What is this? Lambda m naught or lambda m infinity, what is it?
Limiting molar conductivity.
Good. How do you define it?
The molar conductivity of a solution when the concentration approaches zero.
Good. Right. So it is the molar conductivity of a solution at zero concentration or infinite dilution. Right. So that's why we put 0 or infinity. 0 means 0 concentration. Infinity means infinite amount of dilution. So either way, that's going to be fine. So electrolyte and lambda m naught, they have given you a table. So they've given KCl3, KNO3, HCl, CH3COO, and they have given NaCl, and the values are 149.9, 145.0, 426, 426.2, 91.0, at last 126.5. Okay, so this data is given to you, and they're asking you what is lambda m naught or lambda m infinity of CH3COOH. Which area the question is from?
Kohl's law.
Kohl's law.
Yeah. Right. So I don't know whether you know this. See, please understand, people. Kohl's law states that the total limiting molar conductivities is equal to the sum of the individual ions' molar conductivity, limiting molar conductivity. Correct. Right. If you have a mono cation or a mono anion, is no problem. Right. See, something like this, if you have, for example, I want to write I'll just take a general case, right? Say I have lambda m naught of ax by. Right? Now, please understand, now ax by, I will be able to dissociate it as a moles of y plus y moles of b x minus. Right? So if I want to write the limiting molar conductivity, this is how I write. Maybe I'll write it here. So lambda m naught of this will be equal to, now please understand, the stoichiometric coefficient has to be multiplied and the charge has to be divided. Please remember this. Stoichiometric coefficient has to be multiplied and the charge has to be divided, in the sense that you write it as x times lambda m naught of a y plus, but that is not it. You have multiplied the stoichiometric coefficient, but you have to divide it by the charge. So it will be x by y into lambda m naught of a y plus y by x into lambda m naught of b x minus. Again, you see y is the stoichiometric coefficient, x is the charge, so you divide it. Okay, so in this case, you will not find any problem because all of them are going to be monopositive or mono-negative ions, right? But if you have, say, +2 or -2 or whatever it is, at that time you should use this. Okay, right? So if you take a specific example, I don't have space. Maybe I write it here. If I want to do it for Al aluminium sulfate, aluminium Al2SO4 thrice. Right? So I know it will become Al3 plus and SO4 2 minus. So I'll write lambda m naught of this is 2 by 3 into lambda m naught of Al3 plus 3 by 2 into lambda m naught of SO4 2 minus. That's how I write it. Okay, hope you get what I'm saying. Right? The stoichiometric coefficient multiplied, the charge should be divided. Okay. Right. So I think now you can do this question. So they are giving you these values and they're asking you what is the lambda m naught of CH3COOH.
Sir, is it 390.7?
I think it's correct. Right. Okay. So how do we do this problem? Let's see. So I hope there are no questions here. Hope you understood what I'm trying to say. Right. So just how you did thermochemistry, like that you can do here actually. Okay. Right. So what you want is basically CH3COO minus and H plus. Basically lambda m naught of CH3COO minus and lambda m naught of H plus is what you need. Okay. So first we'll check for CH3COO minus. Where is it? So here is what I have. CH3COO minus. I have to take it because I require this. And I require H plus, which is here. So obviously you will add these two values. Now when you add these two values, you will be getting CH3COO minus and H plus, but extra you will be getting Na plus and Cl minus also. So what you have to do, you have to add this two, and here you take it and subtract it. Add these two and subtract this. That's it. So CH3COO minus you got, H plus you got, Na plus and Cl minus you got extra. Now you have Na plus and Cl minus getting subtracted. That's it. So only these three values of use to us. These two are of no use to us. Okay. So it will be 426 plus 0.2 plus 91 divide minus 126.5. So I think you will be getting 390.7 as the lambda m naught of CH3COOH, and this one. Okay. Right. Fine. Next question. See, the first question we solved, that is resistance of one thing is given. What is that? The conductivity, finding molar conductivity, all these things, like it's keep on repeating. These questions are repeating kind of questions. So even though it's easy, but you see it's actually repeating. Okay. Okay, expression. Right. So they have given E naught CR3 plus bar CR is minus 0.74 volts, and E naught MnO4 minus bar Mn2 plus, yeah, Mn2 plus is 1.51 volts, and E naught of Cr2072 minus becoming Cr3 plus is 1.33 volts, and we have given E naught Cl bar Cl minus is 1.36 volts, right? So they're asking which is the strongest oxidizing agent is the question. This was asked in JEE in 2013. Oh, when I wrote. Oh, but I still don't remember the question paper. Right, which is the strongest oxidizing agent? There are choices given to you, but I'm not going to give you the choices. Based on the data, you tell me.
Sir, is it the first one?
First one is,
CR3
so
plus
you have two species here. One is Cr3 plus, one is Cr. Among that, what? But again, that is not the answer, even if you check it. Fine. Okay, maybe I'll give you 10 more seconds for you to think about it. Okay, right. So please understand they're asking about oxidizing agents. I know what oxidizing agents do. They will oxidize something else, but these oxidizing agents undergo reduction. We know this, isn't it? Right. So basically, what I have to look for is ability of the particular species to undergo reduction, is what I have to understand. Is it not? We're talking about oxidizing agents. An oxidizing agent will undergo reduction. We know this, right? So we have to check among these whatever four, right? You have to check for species which will undergo very, very easy reduction. As easy the reduction is, more and more will be the oxidizing.
So then
more
it
and
will
more
be MnO4 minus.
Yes, that's the answer. Right?
The higher
Okay.
potential, higher reduction potential.
Correct. So how will you see? Please understand ability to undergo reduction is directly proportional to the E naught values, positive value. Okay. So more and more is the positive value of the reduction potential. More and more will be the ability of that particular species to undergo reduction. And I can tell it as opposite. Its ability to get oxidized will be directly proportional to the negative value of the E naught. Now, this all comes from this. I know delta G is equal to minus N of E naught. Right? So I know if they want the reaction to be spontaneous, I should have delta G to be less than 0. Correct? Now, I want the reduction to be positive. Actually, I want the reduction to be spontaneous in the sense that I want the reduction reaction to be spontaneous in the sense that delta G should be negative for that. So definitely E should be positive, right? And the ulta for the oxidation process, right? But generally, when we write only potentials, we talk only about the reduction potential, right? So please understand this. The ability to undergo reduction is directly proportional to the positive, more and more positive value of E naught. More and more is the ability of the species to get undergo reduction, right? So now you take just take the maximum positive value. Maximum positive value is here, right? Now again, the question can be which is undergoing reduction. Now if you know MnO4 minus is an oxidizing agent, so you can easily tell it. But if you don't know this, you really have to see which is undergoing reduction, which is undergoing oxidation. Basically, MnO4 minus gets converted to Mn2 plus. Basically, that is my reduction, right? So which is the oxidizing agent here? Oxidizing agent is MnO4 minus. So the answer to this question, which is the strongest oxidizing agent, is MnO4 minus. And if I ask you what is the next, what will be your answer?
CR2.
Cl
also.
minus.
It's Cl. Tell me properly. What is it?
Cl.
Cl. Right. So this is undergoing reduction. So that is my oxidizing agent. So Cl is the what is that? Strong, the second powerful oxidizing agent. After that, it will be Cr2O7 2 minus, and that is Cr3 plus to Cr is happening. That is my oxidation. So we don't have to consider it. I mean Cr3 plus to Cr is reduction, but that is having a negative value. Okay, so maybe we'll do one more question here, like this. Okay, so they have given E naught, basically M2 plus in M3 plus bar M2 plus for the M's are Cr, Mn, iron, and cobalt, and the values are 0. Minus 0.41, and this is 1.57 volts, and this is 0.77 volts plus only, plus only, and this is 1.97 volts. Now they're asking you which metal can easily change its oxidation state, from +2 to +3, right? Which element among these four can easily change its oxidation state from +2 to +3? Now +2 to +3 is oxidation. Hope you remember.
So is it CO?
CO,
CR?
C, CR makes a better answer. Yes, PCR is the answer. Okay, fine. So we are now talking about oxidation, right? So please understand, ability to undergo oxidation is directly proportional to more and more negative value. It's going to be the negative value of the reduction potential. The last time we saw, ability to undergo reduction is directly proportional to the positive value of E naught. For reduction, it is going to be opposite. It's going to be the negative value, right? So whichever is going to have the most negative value, and that can undergo oxidation very easily. Whichever is going to have maximum positive value, that can undergo reduction very easily, right? So there's only one negative value, and that is CR. The answer to this question will be CR, because that is only having a negative value. All the others are having positive values. And if at all I ask you to arrange them in the order of this, arrange the order of easiness. to convert the metal from +2 to +3, obviously the maximum is for Cr. Then all our positive values have to go for the least positive value. Least positive value after that is Fe, and after that it is Mn. And the least capable CO2 plus becoming CO3 plus is almost impossible for cobalt in this 4 things. Okay, this is also going to be the ability to undergo oxidation. Ability to get oxidized, right? Okay, so this kind of questions are very common, right? Okay, next question. This is a very nice question. I like this question. Okay, so they're giving you a cell like this, Zn bar Zn2 plus 1m double bar H plus 1m number platinum H2. This is at 1 bar, right? So the E naught of this is 0.76. Okay, I want to ask you one question. What is the difference between E naught and E? What is the difference?
E naught is under standard conditions.
Okay, fine. What are the standard conditions?
273 Kelvin.
Okay, that is one. Fine. Next.
180
No,
m.
it's actually not 273. 180 is, I'll tell you. Fine. 180 is okay. Then
So 298 Kelvin.
It's room temperature. Okay. All the reactions you do at room temperature. So it's 25 degrees Celsius or it is 298 Kelvin. Okay. So temperature is, so for standard E naught or so standard conditions for E naught is 298 Kelvin, one atmospheric pressure. There is one more.
Volume is 22.
No. That is for gases, right? And that's not, don't confuse STP and this. Right? That STP is different. Right. So one more is all the electrolytes. Right? All the electrolytes should have a concentration of 1 m. Okay. So these three conditions, if it is there, then the potential, whatever you measure, is what is called as your standard reduction potential or standard potential of the cell, whatever it is. Okay. Right. So 298 Kelvin, 1 atmospheric pressure, and all the electrolytes, whatever the electrolyte, zinc sulfate, copper sulfate, HCl, whatever the electrolyte used, all of them must be 1 m concentration. And if at all you use gases like H2, they should have 1 bar pressure. Okay. Or this is almost written here. 1 atm is almost equal to 1 bar. Correct. Right. So these three conditions are there. Okay, fine. This is what I wanted to ask. Okay, fine. So this data is given to you. The cell is given to you. The E naught is given to you. And they're giving you one more. Actually, can I rub this part? Okay. There's one more given to you. They have given PT H2 bar H plus 1 m. Again, this is 1 bar. Double bar Ag plus 1 m bar Ag. This is again 1 m. Okay, we wrote it. And the E naught for this cell is 0.8 volts. Correct? Right. Okay. Now they're asking if I have this cell that is Ag bar Ag plus, which is 0.1 m double bar, zinc 2 plus 0.1 m bar zinc. Okay, now they're asking you the E cell of this, and I want to know whether this cell is spontaneous or not. Or I would say the cell reaction, right? The reaction happening in this cell is spontaneous or not. I have to find. Okay, two things you have to find.
For this thing, we can just say that like E cell should be positive, then it will be spontaneous because minus NFA means like,
Correct.
delta G
Correct.
has to be negative. So.
Absolutely, absolutely. So you have to find this E cell, right? If you find this E cell to be positive, then spontaneous. If you find this E cell to be negative, non-spontaneous. Correct. What you're telling is correct. Right? Go for it. See, this looks like something big, but it's really not. It's very simple. Okay. I'll
So
give you
the
2-3
reaction
minutes.
is spontaneous.
Sorry.
The
Reaction is spontaneous. I don't know how you calculated this, but wait for it. Whatever you have done, I think is wrong. It's not depending on the answer what you told. It's just the amount of time you've taken for this question to answer. That's why I'm telling. Please spend some time. See, I'll give you a small thing. If you want to find E cell for this reaction, you need to know what is the E naught cell of this reaction. I mean, sorry, not reaction. If you want to find E cell of this cell, you need to know what is the E naught of this cell. Then only you can use the Nernst equation here. Remember, for finding E cell, we need to use the Nernst equation. Right? Now, so I have to know what is the E naught cell of this. That is one thing. So fine, you go for it. Let me see how much of understanding you have from what you have learned. So remember, E naught of any given cell can be calculated as, if I give you two sites portions and if I give you the reduction potential values of each element, how will you find the E naught? Hmm?
The E cathode minus real.
Absolutely. Right? So from these two, first find the reduction potential for zinc and the reduction potential for Ag. That you need to find. Right? And then use it here to find the E naught. From that E naught, go for the E cell. That's what you need to do here.
Where is it? 0.04.
0.04
04.
for the whole E cell.
No.
0.04, no, I guess. I think some mistake you're doing, Kana. Let me help you. Wait for it. Let me see if someone else does anything. Okay. So shall I do, or you want some more time? Okay, then I'll do. Right. Fine. So this E naught, how can I write? Right. So it is always going to be E cathode minus E anode, or E right minus E left. Right. So in the right, I basically have E naught H plus bar H2. I have to write only in terms of reduction potential. Please understand. Whatever the bars you write, that should be in terms of reduction. Right. So E naught H plus bar H2, that is in the right, minus E naught Zn2 plus bar Zn. This is how I write. With respect to, see, you see Zn is becoming Zn2 plus, but we are talking about reduction potentials. So we always write like this only. Okay, right. So now this value is given to be 0.76, and I already know what is the value of this E naught H plus bar H2. E naught H plus bar H, 0. That is standard hydrogen electrode. That is my reference point. Okay, so this value is 0, right? So can I say E naught Zn2 plus bar Zn is minus 0.76 volts? One thing you found out.
So, sir, is
right?
it 1.56?
1.56 spontaneous.
Yes, sir.
Okay, we'll check. Right, fine. So this we have found out. So E naught Zn2 plus bar zinc is minus 0.76. Now let me calculate it for Ag. Let me see what happens. Maybe I should, there is my space. Okay, maybe first thing we have done it. Let it up that part. Okay. So, oh my God. Okay, fine. Something fell down. Issues. Okay. So in this, if I write this E naught, I can write it as, so basically my 0.80 is equal to E cathode minus E anode. Basically, I'm going to have E naught Ag plus bar Ag minus E naught H plus bar H2. Again, you see, I'm writing only in terms of reduction, H plus bar H2. Right? Okay. Now this again value is 0. So okay, I can directly get E naught Ag plus bar Ag is 0.8. Okay. Fine. Now what I have to find is the E naught of this one. And then from this E naught, I have to calculate the E cell. Right? Now E naught of this one will be how much? Basically, it will be E right minus E this thing. So it will be E naught of Zn2 plus bar Zn minus of E naught of Ag plus bar Ag, because right minus left. Right? Now both the value we found out now. E naught Zn, these things will become minus 0.76. Minus of E naught Ag plus bar Ag. E naught Ag plus bar Ag, just now we found out to be plus 0.8. So, but there is a negative sign here. So, it will become 0.80. So, what will be the total value? Minus 1.756 volts would be the answer. Not the answer, the E naught. We didn't still get the answer. We are still finding out only E naught. E naught I found to be reduction potential of this minus reduction potential of this. Both the things we found from the previous equation. And that is minus 1.56. Okay, now what I have to find is the E cell. Now I have to go for the Nernst equation. Correct, right? So if I go for the Nernst equation, I know how it looks. E cell is equal to E naught minus, now temperature is not given, and when I know temperature is not given, I take it as 25 degrees Celsius, right? And you will get 0.059 divided by N into log of product by reactant. In the product, you see Ag plus is there. In the reactant, you see Zn2 plus is there, and Ag and Zn are solids. We will not include them. Right? So Ag plus in the products, Zn2 plus in the reactant. So it will be concentration of Ag plus divided by concentration of Zn2 plus. And don't tell me both are 0.1. Are they? Yeah, both are 0.1. So this is 0.1. This is 0.1. So this is log 1. So entirely this is. Are we doing something wrong? Oh. See, small mistakes. Very bad mistakes. See, whenever you are going to write this Nernst equation, whenever you are going to write this term, log of the concentrations, you need to know what is the overall reaction. Right? Overall reaction, how will you write? Say now you see here, Ag is becoming Ag plus by losing an electron, and zinc 2 plus is accepting 2 electrons to form zinc. Now, you cannot just add the two reactions because there are 2 electrons, there is 1 electron here. You have to make sure that in the overall reaction there is no electron present, right? So this into 2 I write, and then I add it. So now what will happen? I have 2Ag plus Zn2 plus becomes 2Ag plus zinc, right? Okay, 2Ag, because I multiplied everything, 2Ag plus Zn2 plus gives 2Ag plus zinc. So now how should I write it? This should be Ag plus concentration squared. Ag plus concentration squared it should be, right? See, in one question, how many things you're learning. That's why I said this is my favorite question. Okay, fine. Now, I know the concentration 0.1. So I can write this particular term as 10 to the power minus 2 divided by 10 to the power minus 1. Right? So overall, this will become 10 to the power minus 1. That's what will happen. Okay. So log of 10 to the power minus 1. Right? Log of 10 to the power minus 1 means this log 10 power minus 1 will come here. So this will basically become E0, E0 plus, now let me write 0.059 as 0.06. 0.06. Now you see the number of electrons involved here are 2. Right? 2 electrons were involved and 2 electrons lost, 2 electrons gained. So 2 is the N. So into, yeah, that's it, right? Now what is the value of E0? E0 I found to be minus 1.56. This will become plus 0.03. So the answer is minus 1.53 volts. Is the answer to this question. Okay, minus 1.53 volts, and the cell reaction is not spontaneous because I'm having a negative sign. Okay, so in one question, you almost used everything possible with respect to your equations, in the sense the E0 cell, E cells. How do you calculate? Okay, so if you just go through it, whatever you've done, right? So initially they have given 2 cells, right? And from the 2 cells, they have given the E0 values. And since one of them was hydrogen electrode, I was able to find the particular element's reduction potential, right? Okay. Now to this cell, right, I calculated the E0 by cathode minus anode. There also cathode minus anode, cathode minus anode. So like this, I found out what is the value of E0 of this cell, which is minus 1.56. Then I have to use the Nernst equation. But before you write the Nernst equation, not only for this question, for any question, you have to get the overall reaction first. This is the overall reaction. And then only you can talk about the number of electrons as well as the powers which are there in the Kc or Qc equation. Right? So then you take the Nernst equation, substitute all the values, then you will be able to find the answer as minus 1.53 volts. I want everybody to say yes if you understood. Did you understand?
Yes, sir.
Yes, sir.
Yes.
Good, good, good. Right? Fine. What is the time? 7:20. Maybe we'll do one more question. Okay.
Sir, for the Nernst equation, like for quick calculations, can we just assume that 0.059 is 0.06?
Absolutely, you can do. No worries at all. Right? 0.059, you can always put it as 0.06. Okay. Right. So now they have given this cell platinum H2 bar HA of 1m concentration, double bar HB 1M bar H2, platinum H2. Okay, this cell is given to us. Okay, now this HA and HB are weak acids, right? HA and HB are weak acids. So generally, how do I write? I directly write it as H2 bar H plus. So in that time, you could have directly taken whatever the concentration was given here. You could have taken the concentration as the direct concentration of H plus, right? But I know this is a weak acid. From this 1M concentration, not all of these 1M are going to come. Some amount of this are going to come, right? So for you to find out, they have given the pKa of HB or HA first, HA to be 3, and pKa of HB, the second acid, is 5, right? So I want you to find what is the E cell of this. Don't get scared. Okay, I know that will be the first thing. Oh my God, pKa, pKbs and all they're asking. Do not worry. You know everything, right? Just try to go for it. Okay, what is the E? If forget about this. Okay, I mean, for this reaction, what would have been the E naught? They're asking to find the E cell. Or further, I need E naught, right? What would have been the E naught for this cell?
0.
0, right? Because again, it's becoming H plus bar H2 or H2 bar H plus, whatever it is. So E naught is 0 for this. The only thing I have to concentrate on is the E cell where E naught is 0. The other part still stays. Go for it. I'll give you maybe 2-3 minutes time for you to think about it. So you have to use equilibrium, ionic equilibrium here.
Sir, should we apply that formula pH equal to pKa plus log of salt?
Log of salt, something like that, but salt concentration will not come. See, look at this. Maybe I'll help you with the pKa and pKb part. How we are going to relate this here. Okay. Right. Now, please understand, guys, for any acid HA, I'm just taking any acid, HA gives some H plus A minus, right? Now, if I take the Ka value, right? Now, Ka value would be concentration of H plus. Now, remember, concentration of H plus and concentration of A minus would be same, right? So, can I write it as concentration of H plus squared? I can write that, right? Concentration of it, because according to stoichiometry, 1 mole of this gives 1 stoichiometric ratios are same, right? So I can write it as concentration of H plus is squared divided by concentration of HA. Done, right? So, okay, let me do it like this. So if I take negative log on both sides, right? So if I take negative log on both sides, so it will this, can I say this will become pKa? Negative log of Ka will become pKa, right? Is equal to, can I say if I take log of this, log A minus log B, it will become, because there is a division part. So now there is as a squared. So I can write it as 2 into pH. Correct? Right? Negative log of.
Sir, it will be the other way
concentration.
around.
What happened?
Sir,
What other
because
way
you're
around?
taking negative of log means it has to be like H has to be
Yeah,
in the
this.
numerator. Like,
Okay, fine. If you're getting confused, let me write it like this. I'll write step by step. So I have negative log of Ka is equal to a negative log of this whole thing. Now I can write it as negative log of H plus a squared plus the negative log of HA. Can I write it like this? Negative log of HA. Already I have a, now this minus this will become, so I have a put a positive sign. Is it okay for you?
so that is what I was saying, sir.
That's what, this is okay, right?
You
Oh,
first you wrote two.
I understand. This is the correct equation. Anyways, calculated, adjusted. Okay, fine. So now negative log of Ka is what is my pKa, and this is squared is there. So I can write it as 2 into pH. pH is negative log of H plus, right? Plus log of the concentration of the acid. I just write log of concentration of the acid, any acid for that matter. Correct, right? Okay, now what I have to understand is, this is how you write it. pKa is equal to pH, or you write as pH is equal to 1 by 2 into pKa minus log of concentration of the acid. I can write it like that. pH is equal to 1 by 2 into pKa minus log of concentration of the acid. Now, in this particular cases you take, right, both the concentration of HA as well as the concentration of HP is 1m, right? So can I say log of 1, this term will not be there in this question, right? Log of 1, this term will not be there in the question. It will become 0 because the concentration of acid is given as 1. So I can directly write pH, which is equal to pKa by 2. Anyways, we'll see how this works. Okay, pH is equal to pKa by 2. Fine. Okay, now this we understood. Hope you understand what I did here. I just took Ka as H plus squared divided by HA. Then I took negative log on both sides. Nothing else. And I got pKa and pH and the log of concentration of acid, which is 0 in this case because the concentration of acid is 1 in both the cases. HA and HP as well as is 1. Okay. Now let me go for the Nernst equation. Let me see how I can fit this in. So I have E cell is equal to E naught, which is 0. We just discussed. So it will be 0.059 divided by what is the number of electrons? Number of electrons, n values where what? N values what? Here.
1.
That's the mistake everybody does. Now please understand, H2 is becoming H plus. And obviously you see it has become 2, or say 2H plus becoming H2 or whatever it is. Now how many electrons? 2 electrons should come. Okay. Not only for this, any standard hydrogen electrode problem, you have to put the number of electron as 2, not 1. Okay. Please keep this in mind because H2 is becoming H plus. Both the hydrogen atoms will become 2H plus. So for that I require 2 electrons, even if I write the opposite reaction. Right. So please understand here the n value is 2 log of, now see, look at this. Now I have, this is my reaction, right? H plus becoming HA plus A minus. Okay, no issues. So log of HA and HP you can leave, right? then you can write it as, so whichever is becoming, well, okay, where is the product? The product is basically going to be HB. Is it? Once again, where is the question? Here. So in the product is HA, because platinum H2 becomes HA and HB becomes platinum H2. So HA is in the product, right? So what I have to understand is concentration of H plus coming from HA, that is the product, right? Divided by concentration of, and it should be squared, isn't it? Because I have 2 H plus. So concentration of H plus is squared coming from HA divided by concentration of H plus coming from HB, right? Squared. Now, guys, if you feel little this thing, you write the overall reaction. Look at this. I have HA becoming H plus coming from HA plus A minus, right? That is what is happening. Am I right? Okay. Now, so we cannot write it like this. I'll write it like this. H2 plus A minus becomes HA, and HB gives H2 plus B minus. This is what is actually given in the reaction. But let me see if there's a better way of writing it. This 3. Okay, what you're doing is correct only. But again, we don't have to confuse ourselves with all these reactions, right? We can just take it. What is the product and what is the this thing, reactant, right? So product by reactant is what we have, right? Okay, fine. So now this, now what? How can I write it? So if I write it here, so this can be written as 0.03, right? Now let me take the logs inside. So this will become negative log of H plus squared, negative log of H plus squared from HA, right? Now I've multiplied the negative sign inside, so this will become positive, negative positive log of H plus squared from HB. One second. Right. So again, this will come here. So this is basically going to be 2 pH. I can write it like this: 0.03 into 2 into pH of HA, right? Minus, now why am I putting a negative sign? Because this is positive. I want negative log for pH. So 2 into pH of HB, right? Okay, now just now we found pH is equal to pK by 2, or pKa is equal to 2 into pH, right? So 2 into pH, I can directly write it as pKa, right? So it is going to be 0.03 into pKa of HA minus pKa of HB is what I have. So 0.03 pKa of HA is 3 minus 5, which will become minus 2 into 0.06. You will get minus, so 2 into minus 0.03 will become minus 0.06 volts. This would have been the answer. Okay, so I think you would have understood the pKa and pH part. If I'll just explain this part again. So this is done. Well, now why am I putting a square? Hope you understand, because H plus becomes 2H plus and H2H plus becomes H2, right? And I have put the two here for the same reason. Okay. Now this I have just multiplied the negative sign inside. Those will become negative log of H plus from HA plus, it should have been negative, but minus into minus becomes plus. So this will become H plus squared from HB. Now this will become 2pH minus log of, minus is already there, so pH I can directly write. Now this has a positive sign, so I will put a negative sign here and write the pH of HB. And just now we calculated pH is equal to pKa by 2, or I can write 2 into pH is equal to pKa. So directly I wrote the pKa values, and I found the answer to be minus 0.06. Okay, guys, understood what we did here? Right, we just included one more concept from equilibrium and nothing else. Rest all are same. Okay, hope you understood. What is the time? Okay, took extra time. Okay, fine. If you have no doubts, we can wind up here. Is it okay?
Yes.
Fine. Good. Thank you so much. We'll meet again tomorrow.
Thank you, sir.
Thank you, sir.
Thank you.